Okay, so we have seen how isolated singularities are very important, and so for isolated singularities, there's a Laurent series expansion available, and among all the coefficients that come up when you have a Laurent series expansion, there is one coefficient which is of great importance, and that is called the residue. Right. So in this lecture, we will take a closer look at the residue and how to compute residue, considering several examples. Okay, so the Laurent expansion looks something like this. So there is the regular part A0 plus A1 times Z minus Z0 plus so on, and then there is the singularity part B1 over Z minus Z0, B2 over Z minus Z0, the whole square, and so on. Right? Among all of these coefficients, B1 occupies a central spotlight, right? So it has this very important value associated with it, right? So and that's called the residue, right? So let's look at how we can come up with sort of an algorithm to work out the residue for function given some singularity, isolated singularity. So in particular, our discussion will be to identify or to work out these residues at poles, right? Poles are the most frequently encountered kind of singularities. So essential singularities are sort of pathological, but and again removable singularities are removable, therefore they're not so exciting. On the other hand, poles have this they appear repeatedly, and they're also there's a prescription that we can write down, and that's what we will do in this lecture. So one way to identify a pole is to keep on finding successive limits of this kind. So you just multiply by Z minus Z0, and f of z you have identified as an isolated singularity. So you multiply by Z minus Z0, and then try to evaluate this limit Z going to Z0. And if you find that this limit does not exist, then try to find Z minus Z0 squared times f of z and take the limit Z minus Z0. Even if this limit does not exist, go to the next order and so on. The smallest integer m for which this limit is finite would be the order of the pole, right? So this is often, so this kind of a sort of trial and error method is often quite a practical way to work out the order of a pole. So having identified this pole, how do you work out the residue, right? So these are the two aspects which we would often have to worry about and find answers to. One is what is the order of a pole, and the second is what is the residue at that point, right? So to find the residue, so we observe that if you multiply this function f of z by z minus z0 the whole power m, right? So since it is a residue of order, it's a pole of order m, so which means that there are no terms beyond bm, so there's no bm plus 1 so on, so it ends at that point bm. So if you multiply this function by z minus z0 the whole power m, so indeed the entire thing becomes regular, right, as we have seen. So this is this is an analytic function. So basically it's a Taylor expansion as far as this function is concerned. And so now if you want to, from this function, this is a very nice smooth function, an analytic function you have, and from this function what can you do to this function to pull out this coefficient b1? It's b1 which we care about. That's the residue. So the way to find b1 is of course to successively differentiate this function m minus 1 times. So if you differentiate it once, and then this bm will go away. Then if you differentiate it a second time, bm minus 1 will go away. And the third time, bm m minus 2 so on will keep on going away. And then if you successively differentiate it m minus 1 times, you will be left with just this constant b1, but with this factor which is b m minus 1 the whole factorial, right? And all these higher order terms you can put them to 0 by just taking the limit z going to 0, because all of these terms which appear before b1 will have at least one factor of z minus z0. So if you put z equal to z0, all of them will vanish. And as far as this constant, so b1 will be just a constant, but attached along with it will be m minus 1 factorial. So therefore, the prescription for finding the residue of an mth order pole is to do just this: take the m minus 1th derivative, and at this point take the value of this function at z equal to z0, and then divide by m minus 1 factorial, and you're done. Right? So this is a easy enough prescription to write down. Not necessarily always the easiest way to work it out, but there is a ready prescription available. Right? So let's look at some examples where how do we actually compute these residues. Okay, so first example is a function of this kind, very simple, z plus 1 divided by z squared plus 9. So the denominator is basically z plus 3i into z minus 3i. So there are two poles. One of them is at 3i and the other one is at minus 3i. And both of these are evidently simple poles, because if you simply multiply by z plus 3i or by z minus 3i, that pole is gone, right? So it's a simple pole, each of them. So, and the residues at these points are simply given by, if you want to evaluate it at z equal to 3i, so just multiply by z minus 3i and then put the value z equal to 3i, and you're done. So and that gives you the residue to be half minus 1 by 6i. And on the other hand, if you want to evaluate the residue at the point z equal to minus 3i, you multiply by z plus 3i and put the value z equal to minus 3i, and this gives for you a residue of half plus 1 by 6i. Right? A straightforward example. So look at another example. So if you consider a function like this, z cube plus 2z, so you have some polynomial sitting in the numerator and z minus I the whole cube in the denominator. Right? So it's certainly a pole, right? Because if you put z equal to I, you immediately see that there is a singularity there, and it's of course isolated. And if you have a scenario like this, then it's useful to just define a function phi of z, and so you think of f of z as some function phi of z divided by z minus I the whole cube, and where phi of z is z cube plus 2z. It's just a polynomial, so it's entire, and phi of I is non-zero, so it's not of a 0 by 0 form. Right? So then we conclude that indeed this function has a pole of order 3 at z equal to I, and the residue is given by this prescription we have. So you have to take the second derivative of this numerator phi of z. Right, phi of z is of course obtained by multiplying f of z by z minus I the whole cube. Right? So that's what you're supposed to do, which is to multiply by this factor, which is the power is basically the order of the pole, so which is already done, phi of z. So if you take the second derivative of this, you get 3z squared, then 6z, and then you have to evaluate this at the point I, so you get 6i divided by 2 factorial. So the answer is just 3i. Right? So this is the residue of this function at the point z equal to I. Now if you consider this function 1 over z times e to the z minus 1. So oftentimes it is simplest to actually just find the expansion of the Laurent's expansion of this function, which in turn can be actually got from the Taylor expansion of the denominator. If you just simply do that, you can work out the order of the pole and also to work out the residue. Right? So in this case, for example, you see that the function f of z can be written as 1 over z times this e to the z. This 1 goes away, and so you're left with just z over 1 factorial plus z squared plus divided by 2 factorial plus z cubed by 3 factorial plus so on. And then you can actually pull out this 1 over z from the second of these functions, and then so you get 1 over z squared times a function which is clearly does not have a singularity at the point z equal to 0. So basically you have a singularity at z equal to 0, then you are able to pull out this 1 over z from this second function, 1 over e to the z minus 1, and so therefore it's evident that this has a pole of order 2, because this other function, which you can call phi of z, so you can think of f of z as phi of z divided by z squared, where you only know this function phi of z in terms of this complicated looking expansion, but it's evident that there is no pole for this function at z equal to 0. Right? So which you can see by checking, by directly putting z equals 0, it will just be 1. So this function phi of z is 1 over 1 plus z by 2, 2 factorial plus z squared by 3 factorial and so on. So now this function, you can take a derivative of this, right? So we go back to our description. So you have to, since it's a pole of order 2, you have to take a derivative of this function and then put z equals 0. So the way to take a derivative of this complicated looking function is to use the quotient rule. So if you have 1 over some function, what you do is u over v, it's v du minus u dv. So in this case, v du will be just 0, so it's just minus u dv, so which is minus of 1 over this stuff times the derivative of the denominator. So the derivative of the denominator will be just 1 over 2 factorial plus 2z by 3 factorial plus 3 squared by 4 factorial and so on, and the denominator has to be squared, and you have to take the value of this at the point z equals 0. So you see that the denominator will just get reduced to 1, and you take this limit, and then the numerator is going to give you just a minus half. So that's the residue of this function at the point z equals 0. So there are other ways of evaluating the residue for this function, and we can cross check it. But basically, this is a direct way. You just simply expand, find the Taylor series expansion of the denominator, and then argue from first principles that the residue for this function is just minus half. Now, zeros of analytic functions are intimately connected to these poles, right? So in fact, if you look at functions which are of the form numerator by divided, they are denominator, and if the denominator has 0 of a certain order, then that will lead to a pole of the same order, provided the numerator has no mess in it, right? So let's define this carefully. A function f of z that's analytic at a point z0 is said to have a 0 of order m at z0 if, first of all, f of z0 must be 0, and it's not just 0, but it's a 0 of order m. So what that means is that you'll be able to write down f of z as z minus z0 to the power m times g of z, where g of z is an analytic function which does not become 0 at the point z equals 0, right? So that's important. So g of z is analytic at z0, and it's also non-zero at z0, and so you should be able to sort of pull out this factor z minus z0 the whole power m, and so then you say that it's a 0 of order m, right? So for example, this polynomial z squared minus 4, you can write it as z plus 2 times z minus 2, so it has zeros at plus 2 and at minus 2, each of order 1, right? So it's the definition is very analogous to the kind of definition we have for the order of a pole. Okay, so if you have a function like z times sine of z, it has a 0 of order 2 at the origin, because z will contribute one order and sine of z contributes the other. So another way to think of this is to just find the value of the function and find the value of the derivative at that point. So f of 0 is 0, f prime of 0 is also 0, but f double prime of 0 is non-zero. So find the first derivative at that point which is non-zero, and so that will be the order of the 0 plus 1, right? So that's also another way of arriving at the same answer for the order of a 0. So we can express this function as f of z is equal to z squared times g of z, but g of z is, you have to be careful about how you define this g of z, right? So this is a way of defining this function where the singularity has been removed, right? We have seen this. So g of z must be defined as sine z over z for all z not equal to 0, and it's defined as 1 at z equal to 0. It's an analytic function, we have seen this, and it is non-zero at the point as z equals 0. It's explicitly non-zero, and we have pulled out z squared, just like how the definition for the order of zeros was given. Now, so why do we care about such zeros of function? Because of their connection to poles, right? So we have this couple of results which are very useful. So one of them is that if you have two functions p of z and q of z, and both are analytic at a point z0, such that p of z0 is not 0. So the numerator does not have a 0 at that point, whereas the denominator has a 0, right? So if the denominator has a 0 at a certain point, then of course you have a pole at that point, right? It has a 0 of order m, so then the statement is that the quotient function f of z is equal to p of z divided by q of z is going to have a pole of order m at that point, right? So it seems straightforward enough to that this is the case, right? It is possible to argue for this a little more rigorously, but I think it's quite intuitive that if you have a function p of z which is not 0 at this point, and the denominator q of z has a 0 of a certain order, then the overall function f of z has a pole of order m at that point z naught. So let's look at an example. So if you take two functions like p of z and q of z, one of them here is p of z is just 1, it's an entire function, it's constant. Q of z is z times e to the z minus 1. Now both of them are actually entire, and so you should divide one by the other, so 1 over z times e to the z minus 1. Then the pole that is there at the origin can be extracted from the order of the 0 of the denominator, right? So we have already seen that z times e to the we can argue that z times e to the z minus 1 has a 0 of order 2, just like we argued that z times sine z has a 0 of order 2 at the origin. So likewise, z times e to the z minus 1 also has a 0 of order 2 at the origin. Therefore, this function 1 over z times e to the z minus 1 has a pole of order 2. As we have already seen, we worked this out from first principles, but we can also argue based on this result. So there is another result which is very useful, and that is that p of z and q of z, if there are two functions that are both analytic at a point z naught, such that p of z naught is not 0 and q of z naught is 0, so the denominator is 0, the numerator is not 0, and if you are able to find that q prime of z naught is not 0, right? So the derivative of the denominator is not 0, then you're guaranteed that z naught is a simple pole of the quotient function. So now you take this quotient function p of z divided by q of z, and then you can simply write down the residue also straight away. And so the residue is simply given by p of z naught divided by q prime of z naught, right? So if you are able to be sure that this function f of z has a simple pole, then you simply work out p of z naught and then divide it by q prime of z naught and you're done, right? So the reason this works out like here is because after all, residue of this function f of z at z equal to z naught is basically residue of this function p of z divided by z minus z naught times u z. Since the denominator has a pole of order, the denominator has a 0 of order 1. The reason is because q prime of z naught is not 0. So that immediately means that you'll be able to write down the denominator as z minus z naught times g of z, and so now it's a matter of simply multiplying this function by z minus z naught, and then you just have to take the limit of z going to z naught, right? But g of z naught is actually nothing but q prime of z naught, right? So this is also something which directly comes from the definition of this 0 of order 1, right? After all, you're given that you have a function q of z and it has a 0, so you're able to pull out z minus z naught, and then you're also given that q prime is not 0. Therefore, indeed, g of z naught is nothing but q prime of z naught. So that's all. So this is a straightforward result, and it is useful to just directly invoke this result and to work out residues. For example, if you have a function like cos z divided by sine z, now sine z has a bunch of zeros which are sitting on the real axis, so they are located at n pi, and all of these are isolated singularities, and they're all zeros. They're zeros of sine z and singularities of cot z, and so the way to work out, using this previous result, the way to work out the residue is to first find out p of n pi, which is minus 1 to the n, right? So you have to just put cosine of n pi, which will be minus 1 to the n, which is not 0, right? So that first condition is met. Q of n pi is 0, so after all it is a 0 at that point. N pi is a 0 of the function sine z, and q prime of n pi, which is just cosine of n pi, is again minus 1 to the n, which is not 0. So each of the singularities z equal to n pi is a simple pole, and the residue is simply given by p of n pi divided by q prime of n pi, which are actually both the same in this particular case, and so therefore the residue is just 1. Right? So we have directly invoked this result. You could also work this out from first principles. Let's look at just one more example. And so if you have tan of z divided by z squared, now you can write this as sine of z divided by z squared times cosine of z. Suppose we focus on the point z equal to pi by 2, right? So the singularity here comes because cosine of pi by 2 is a 0. So z equal to pi by 2 is a 0 of the cosine function. So sine of z and z squared are well behaved at this point. So you can actually define this function f of z to be p of z over q of z, where p of z is sine z divided by z squared. So since you are at z equal to pi by 2, there is no problem with this function sine z by z squared. It would be problematic if you are looking at it at the origin. And q of z is equal to cosine z. So the mess really comes from cosine of z, which has a 0 at the point pi by 2. Now, since p of pi by 2 is simply sine of pi by 2 by z squared. Sine of pi by 2 is 1, z squared is pi squared by 4, so it's 4 by pi squared, which is non-zero. Q of pi by 2 is 0, q prime of pi by 2 is minus 1, right? It's minus sine of z, and at pi by 2 minus 1, which is non-zero. The singularity at z equal to pi by 2 is a simple pole, and whose residue is given by just this result that we have written down, p of pi by 2 divided by q prime of pi by 2, which is 4 by pi squared divided by minus 1. So the answer is minus 4 by pi squared. So why do we care so much about the residue? This is something that we will discuss in the upcoming lectures. But in this lecture, we saw a bunch of different methods for evaluating these residues of functions whenever there is a singularity or an isolated singularity, and in particular for poles of order n. Okay, thank you.